All right, get ready, because we're diving deep into the future of flight.
Yeah.
You sent over some seriously cool research on high aspect ratio wings.
Yeah, it's from a paper published this year in Progress in Aerospace Sciences. Cutting edge stuff.
We're talking designs that could totally change how planes look and fly.
Yeah, for sure.
So we're on a mission today. We're going to figure out why these high aspect ratio wings are such a big deal.
Okay.
What are the benefits? What are the challenges? And get this.
Right.
Some of these planes look straight out of a sci-fi movie. I'm not kidding.
Yeah, some of the designs are pretty wild, but the science behind them, it's solid.
Okay, so first things first. Why is everyone so obsessed with making planes more efficient these days?
Well, we're all becoming more aware of our impact on the environment.
Right.
And, aviation has a pretty big carbon footprint.
Yeah.
Plus, fuel costs. Huge expense for airlines, so any way to burn less fuel saves them a ton of money.
Makes sense. So this paper, it digs into how reducing something called lift-induced drag is key to making planes more efficient.
Mm-hmm.
And that's where wing aspect ratio comes in. Now, I'm guessing aspect ratio is more than just how big the wings are, right?
Yeah, you got it. It's really about the shape. Think of it like this. A glider with its long, slender wings, that's a high aspect ratio. But a fighter jet with those short, stubby wings, that's a low aspect ratio.
Okay, so basically the longer and skinnier the wing, the higher the aspect ratio.
Right?
And the higher the aspect ratio, the less drag. But just how much of a difference does that make in terms of fuel savings? Like, what are we talking about here?
A huge difference. This paper mentions that for a plane like an Airbus A320, lift-induced drag can be up to 80% of the total drag during climbs.
80%?
Yeah.
No wonder everyone's trying to crack this aspect ratio puzzle. So they're aiming for what they call HARW and UHARW. I'm guessing those stand for high and ultra-high aspect ratio wings.
You're right on the money. And we're already seeing this trend in modern aircraft. The Boeing 787 and Airbus A350, for instance, have aspect ratios of close to or even over 10.
Wow.
Which is significantly higher than older planes.
So we're already seeing these longer, thinner wings out there.
Mm-hmm.
Are there any planes pushing the limits even further?
Oh, absolutely. Unmanned aerial vehicles, UAVs, and sailplanes are leading the way. The Northrop Grumman RQ-4 Global Hawk, a surveillance UAV, boasts an aspect ratio of 25.
25.
And the Airbus Zephyr, a solar-powered pseudo-satellite, can stay aloft for months thanks to its high aspect ratio wings.
Months? That's insane. It must look like a giant kite floating up there, but I guess you can't exactly fit a whole bunch of passengers in a plane designed like that.
Right, and that brings us to a crucial point. The optimal aspect ratio isn't a one-size-fits-all solution. It depends on what you're trying to achieve.
So it's not just about making the wings as long and thin as possible.
Not necessarily. You have to consider other factors like weight, structural strength, and operating costs. For example, the ideal aspect ratio for minimizing fuel burn might be different from the ideal ratio for minimizing the overall cost of operating an aircraft.
Ah, so there's a trade-off. What else affects that sweet spot?
Well, things like new flow control technologies can impact it too.
Yeah.
Some of these technologies can actually smooth out the airflow over the wing, reducing what we call parasite drag. So the optimal aspect ratio can change depending on how much you can reduce that parasite drag with these technologies.
Okay, so it's a complex equation. It's not just about making wings as long and skinny as possible. But then the paper gets into the limitations of traditional wing designs, particularly when you start talking about those super high aspect ratios. What are the main challenges there?
The biggest one is that as wings get longer and thinner, they experience more stress during flight. It's all about the bending moments, which are basically forces that try to bend the wing. So you need a stronger, heavier structure to handle those stresses.
Right. And that extra weight works against your goal of being fuel efficient.
That's a catch-22. You want long wings for efficiency, but those long wings need extra support that makes them heavier. What a conundrum.
Exactly. And that's why researchers are exploring some seriously unconventional wing designs.
Okay.
Looking for ways to provide that support without all the extra weight. They're thinking outside the box, literally.
Okay, now we're talking. This is where things get really interesting. One design that caught my eye is the Strut-Braced wing. I'm picturing something like a biplane, but more modern. Am I on the right track?
Sort of. Imagine a main wing connected to the fuselage, like on a regular plane, but with an extra strut, almost like a leg, connecting the wing to the fuselage further down. This strut helps support the wing and reduces those intense bending forces it experiences.
Ah, so it's like giving the wing an extra arm to lean on. What are the benefits of that? Well, since the strut is helping to carry the load, the wing itself can be thinner. Thinner wings mean less drag, which is especially important at higher speeds. Plus, this design could potentially allow for smoother airflow over the wing, which, as we talked about earlier, can really boost efficiency.
So strut-braced wings could be a game changer. Is anyone actually working on this technology?
Oh, absolutely. NASA and Boeing have been collaborating on strut-braced wing research for a while now. They even have a project called Sugar Subsonic Ultra-Green Aircraft Research, and they're estimating this design could reduce fuel burn by a whopping 30 to 60% compared to conventional aircraft.
Now that's what I call progress. And to think, this idea was first floated back in the 1950s. Talk about ahead of its time. Just how much longer can these strut-braced wings be compared to a regular wing?
Hold on to your hat because the span of a strut-braced wing can be about 50% longer than a cantilever wing on a similar aircraft. That's a pretty dramatic difference.
Wow, that IS, huge. Okay, so strut-braced wings are looking pretty promising. But the paper also mentions another wild concept, twin-fuselage aircraft. This one really sounds like something straight out of a sci-fi movie. Can you paint a picture of what that looks like?
Picture this. Instead of one fuselage, you have two connected by a giant wing that stretches between them.
So basically, two planes mashed together. Yeah. How does that even work?
It's all about spreading the load differently. With two fuselages, you essentially create a more balanced structure,
Okay.
which helps minimize those bending forces on the wing.
So it's like having two shoulders to carry a heavy weight instead of just one.
Exactly. And this isn't a totally new idea either. Decades ago, NASA was even experimenting with large cargo aircraft that had a twin fuselage design, but it never really took off for passenger planes.
I'm guessing there were some major roadblocks back then.
Definitely. There were issues with how the plane would handle in flight. And airports just weren't designed to accommodate these double-bodied planes. Runways weren't wide enough, terminals weren't set up to handle them.
So it was ahead of its time, kind of like a technological time traveler. But now, with advancements in materials and airport infrastructure, could twin fuselage aircraft be making a comeback?
You bet. There's a resurgence of interest in this design, driven by advancements in lightweight composite materials and those clever folding wingtips. In fact, Airbus has already patented a twin fuselage design that incorporates those folding wingtips.
Okay, that's some serious innovation. But how do these twin fuselage planes stack up against the strut-braced wings when it comes to fuel efficiency? Which one wins the efficiency race?
Well, research from the RHEA project, which is all about designing ultra-high aspect ratio wings, suggests that twin fuselage aircraft might actually outperform strut-braced wing aircraft when it comes to fuel savings.
Interesting.
Especially for those long-haul flights.
So it's neck and neck. It's like we're witnessing a design duel between two titans of aviation innovation.
I love that analogy. And both designs have the potential to completely change the way we fly.
Okay, now I have to ask about those folding wingtips. I know they're not new. We've seen them on the Boeing 777 for a while now, but it sounds like they're evolving into something way more sophisticated. What's the latest on those?
You're right. Folding wingtips are becoming much more than just a way to squeeze those big planes into airport gates. Researchers are figuring out how to use them to actually adjust the wing's aspect ratio on the fly, so to speak, for different phases of flight.
So you're telling me that we could have planes with wings that change shape in midair? That's straight out of a superhero movie. What would be the benefit of doing that?
Well, think about it. During takeoff and landing, you don't need that super long wingspan.
Right?
But for efficient cruising, you do. So being able to adjust the aspect ratio for different phases of flight could lead to some pretty significant gains in efficiency.
That's incredible. So how do they actually make these wingtips fold and unfold with such precision? Are we talking hydraulics, motors, tiny little elves with wrenches?
I wish. No, it's actually this cool concept called the semi-aeroelastic hinge, or SAH for short. It allows the wingtips to either rotate freely or lock into a specific position for optimal cruising.
Okay, so it's like a super smart hinge. And is it just a theoretical concept, or is anyone actually building planes with this technology?
Airbus has actually flown a demonstrator aircraft called the Albatross Zone, which successfully tested this SAH concept in flight. They're really pushing the boundaries.
So it's not just science fiction anymore, it's becoming reality. And speaking of innovative designs, I read about another cool idea using fuel tanks at the wingtips. How does that tie into all of this?
That's a really clever approach to optimizing weight distribution. By strategically placing fuel tanks out on the wingtips, you can actually counterbalance some of the weight of the fuselage and reduce stress on the wings during flight.
So it's like a high-tech balancing act. And all of these innovations, from strut-braced wings to twin-fuselage aircraft to shape-shifting wingtips, point to a pretty exciting future for aviation, don't they?
Absolutely. We're potentially on the cusp of a revolution in aircraft design,
Yeah.
with the goal of making air travel much more sustainable and efficient. But of course, it's not all smooth flying from here. There are still some serious design challenges to overcome.
Okay, let's dive into those challenges. What are the biggest hurdles facing these next-generation aircraft designs?
Well, with these radical new wing designs, aerodynamics gets a whole lot trickier. Think about it. Those super long, slender wings are like giant sails. Catching the wind and managing that airflow is a real challenge, especially at higher speeds.
So it's not just about slapping on some longer wings and calling it a day. What are some of the specific aerodynamic issues they have to deal with?
One big one is something called airflow separation. Imagine you're holding a piece of paper out a car window at a certain speed. The air no longer flows smoothly over the paper and it starts to flap around. That's kind of what can happen with these long wings, and it creates a lot of drag.
Okay, that makes sense. And the paper also mentions something called unsteady aerodynamic loads. What are those and why are they a problem?
Imagine that same piece of paper out the car window, but now picture the wind gusting and swirling. The forces on that paper are constantly changing, and that's what we mean by unsteady aerodynamic loads. It's like trying to fly a kite in a hurricane. And those changing forces can make it really hard to predict how the wing will behave and keep the plane stable.
Yikes. That sounds like a recipe for disaster.
Hmm.
And I bet those unconventional wing designs, like the strut-braced wings and the twin fuselage planes, make things even more complicated, right?
You're absolutely right. Those struts and extra fuselages create all sorts of interesting aerodynamic interactions that engineers have to figure out. It's like adding more instruments to an orchestra. You have to make sure they're all playing in harmony.
So it's a complex symphony of airflow and forces. And then there's that whole issue of aeroelasticity, which, if I remember correctly, is all about how the wings flex and bend during flight. And I remember reading something about flutter being a particular concern
Hmm.
with these high aspect ratio wings.
Ah, yes. Flutter. That's the one you don't want to experience in midair. Think of a guitar string vibrating. If it vibrates at just the right frequency, it can create a sound. Well, with wings, if they vibrate at a certain frequency due to the airflow, it can create something called flutter, which is basically a very dangerous and destructive vibration.
So it's like the wings are trying to play a heavy metal song when you'd rather be listening to smooth jazz.
Exactly. And the longer and thinner the wings, the more prone they are to this kind of vibration. It's like trying to play a really long, thin guitar string. It's going to wobble all over the place.
So how do engineers prevent these wings from turning into giant, out-of-tune guitars?
It requires a deep understanding of both the aerodynamics and the structural mechanics of the wing. They have to predict how the airflow will affect the wing's shape and how the wing's flexibility will, in turn, affect the airflow. It's a very complex dance.
So it's not just about designing a wing that's strong enough. It's about designing a wing that can handle those aerodynamic forces and vibrations without falling apart. No pressure engineers.
Right. And on top of that, they're also striving for something called aerostructural optimization.
Now, we've touched on this term a couple of times, but I think it's worth explaining in a bit more detail. What does it mean to optimize a wing, both aerodynamically and structurally?
It's like finding the perfect balance between beauty and brains. Aerostructural optimization means designing the wing's shape and internal structure simultaneously to achieve the best possible performance. It's like sculpting a work of art that's also incredibly strong and functional.
So it's about creating a wing that's not only efficient in terms of how it slices through the air, but also lightweight and strong enough to handle the stresses of flight. It sounds like a pretty tall order.
It definitely is. And with these unconventional wing designs, it becomes even more challenging. Remember those struts on the strut-braced wing? Well, you have to make sure those struts not only provide support, but also don't disrupt the airflow too much. And with the twin-fuselage aircraft, you have to figure out how those two fuselages interact with the airflow around the wing.
So it's all about finding that sweet spot where everything works together in perfect harmony. But all of this sounds very theoretical. How do they actually test these radical wing designs to make sure they work in the real world?
Well, the good old wind tunnel is still a vital tool. They build scale models of these aircraft and put them in wind tunnels to see how the air flows over them. They can visualize those aerodynamic forces and make adjustments to the design as needed.
So it's like giving those designs a test drive in a controlled environment before letting them loose in the wild blue yonder.
Exactly. And then, of course, there are flight tests. They actually build full-scale prototypes and fly them together real-world data on how the aircraft performs.
So it's a combination of computer simulations, wind tunnel testing, and good old-fashioned flight testing. It's like taking a car from the drawing board to the test track to the showroom floor.
That's a great analogy. And through it all, they're constantly collecting data and refining the designs, pushing the boundaries of what's possible.
It's really remarkable how far aircraft design has come. It wasn't that long ago that people thought flying was impossible, and now we're talking about planes with wings that change shape in midair.
I know, it's like we're living in the future. But before we get too carried away with all this futuristic talk, let's get back to those specific wing designs and see how they stack up against each other. Where do things stand right now with each of these concepts?
Sounds good to me. Let's take a closer look at the research findings and see which designs are leading the pack in the race for more efficient flight. All right, let's break down the contenders in this efficiency showdown, starting with the classic tube and wing design with those familiar cantilever wings. What's the latest on those?
Well, the research suggests that for this type of aircraft, the sweet spot for minimizing operating costs is an aspect ratio somewhere between 10 and 12.
So we're already seeing planes like the Boeing 787 and Airbus A350 pushing close to that limit, right?
Exactly. Those aircraft are already incorporating some pretty impressive technology to improve efficiency. But if we want to go beyond that 10 to 12 range, we start running into those weight limitations we talked about earlier.
Right, those wings get so long and thin that you need a super heavy structure to support them, which kind of defeats the purpose of trying to be fuel efficient.
Exactly. It's like trying to build a bridge out of toothpicks. Eventually, it's just not going to hold up. So that's where those unconventional designs come in, offering a way to break through that barrier.
Okay, let's talk about those unconventional designs, starting with the strut-braced wings. What's the consensus on their potential?
The research on strut-braced wings is really exciting. The paper cites studies that estimate fuel burn reductions of anywhere from 30 to 60% compared to conventional aircraft.
Wow, 30 to 60%. That's a huge potential improvement. What kind of aspect ratios are we talking about with these designs?
The research suggests that even without factoring in other fancy technologies, strut-braced wings can achieve an optimal aspect ratio of somewhere between 14 and 20 for minimum fuel burn.
So they're already surpassing those conventional designs.
Yes, and when you start adding in things like natural laminar flow, which smooths out the airflow over the wing, or advanced composite materials, which are lighter and stronger, the optimal aspect ratio could potentially climb even higher to between 19 and 26.
That's a lot of wing. And this isn't just theoretical, right? Are companies actually investing in this technology?
Absolutely. Boeing recently snagged a massive $725 million contract to build a demonstrator aircraft with a strut-braced wing. They're clearly betting big on this concept.
And with good reason.
Okay.
Okay, so strut-braced wings are looking like a strong contender.
While strut-braced wings seem to be getting more attention from industry right now, the research on twin-fuselage aircraft is really compelling, especially for longer flights. Remember the RHEA project we mentioned? Well, they found that these twin-fuselage designs could be even more efficient than strut-braced wings for those medium and long-range missions.
So it's a close race. It's like we're seeing two different paths to the same destination. More efficient flight.
That's a great way to put it. And then, of course, we have those evolving folding wingtips, which could potentially be incorporated into both conventional and unconventional designs.
Right. Those folding wingtips seem like they could be a game changer in terms of flexibility and efficiency. It's like having the best of both worlds.
Exactly. And the research backs that up. Studies show that folding wingtips can significantly reduce wing weight, decrease those pesky bending forces, and even increase the aircraft's range by more than 5%.
So it's a win-win-win situation. But I seem to remember the paper mentioning some challenges with folding wingtips too, right?
Of course, there are always challenges. Implementing folding wingtips effectively requires a lot of careful consideration. You have to make sure they're strong enough to handle the stresses of flight and that they don't create extra drag when they're unfolded.
Right. It's like designing a transformer. You have to make sure it looks good and functions well in both modes.
Exactly. And there are also some logistical hurdles to overcome. Aircraft manufacturers, regulatory agencies, and airport operators all need to be on the same page to make sure these folding wingtips can be safely integrated into the existing aviation system.
So it's a complex puzzle with a lot of moving pieces. But beyond these leading contenders, the research also hinted at some even more out there designs. What else is brewing on the cutting edge?
Well, one concept that's particularly fascinating is the truss-braced wing. It takes the strut-braced wing concept and cranks it up a notch.
Okay, I'm intrigued. How does it work?
Instead of just one strut supporting the wing, it uses a whole network of interconnected struts called a truss. Imagine a bridge or a tower crane. Those use truss structures for strength and stability.
Ah, so it's like giving the wing a whole scaffolding system for support. What's the advantage of that?
Well, it allows for even greater increases in wingspan and potentially even thinner wing designs. It's all about squeezing out every bit of efficiency by maximizing that aspect ratio while still making sure the wing can handle the load.
So it's like building a super strong, super light wing that can stretch out forever. Is anyone actually working on this truss-braced wing concept?
You bet. NASA and Boeing are both heavily involved in researching and testing truss-braced wing designs as part of that sugar project we talked about. They're running simulations, conducting wind tunnel tests, and even building a full-scale demonstrator aircraft.
Wow, they're not messing around. What kind of efficiency gains are they hoping to achieve with this truss-braced wing?
Early estimates from the Sugar Project suggest a truss-braced wing combined with other advanced technologies could reduce fuel burn by a staggering 64% compared to a 2005 baseline aircraft.
64%. Now that's what I call progress. But like with any radical new design, there must be some major challenges, right?
Definitely. One of the biggest hurdles is the sheer complexity of the structure. Designing and building a truss-braced wing that's both strong and lightweight requires some serious engineering ingenuity. And then there's the aerodynamics. That truss structure itself can create drag, so minimizing that interference is crucial.
All right, it's a delicate balancing act. So it sounds like the truss-braced wing is still very much in the experimental phase.
It is, but the research is moving quickly. And with big players like Boeing and NASA investing heavily in this technology, it wouldn't surprise me to see truss-braced wing aircraft gracing the skies in the not-too-distant future.
Okay, truss-braced wings, check. What other unusual suspects are on the horizon?
Well, there's one concept that's really captured the imagination of aerospace engineers: the blended wing body.
Blended wing body. That sounds like something out of a sci-fi movie. What is that exactly?
Imagine an aircraft where the wings seamlessly blend into the fuselage, creating a single continuous lifting surface.
So kind of like a flying wing, but even more integrated. I'm picturing something super sleek and futuristic.
You got it. The idea behind this design is to maximize lift and minimize drag. By getting rid of that distinct boxy fuselage and merging it with the wings, you reduce the overall surface area, which means less friction and a smoother ride through the air.
And less drag means more efficiency. But I imagine designing an aircraft like that is incredibly complex.
Oh, absolutely. Creating a blended wing body that's structurally sound, aerodynamically stable, and able to accommodate passengers and cargo is a monumental challenge.
And then there's the whole passenger experience to consider. Sitting in a giant wing might not be everyone's idea of a comfortable flight.
That's a good point. There are definitely concerns about things like passenger comfort window placement and even emergency evacuation procedures in a blended wing body design. It's not just about the engineering, it's about the human factor as well.
Right, you have to make sure it's not only efficient, but also safe and enjoyable for the people on board. So it sounds like the blended wing body is still a long way from becoming a reality.
It is. But despite the challenges, the potential benefits are so enticing that several research institutions, including NASA, are actively exploring this concept. It's definitely a design to keep an eye on.
Okay, blended wing body, filed away for future deep dives.
Yeah.
Anything else on your radar?
Well, there's a whole world of bio-inspired designs out there, drawing inspiration from nature's best flyers.
Ah, biomimicry. I love it. Nature has been perfecting flight for millions of years. So why not learn from the best? What kind of designs are we talking about here?
Researchers are studying everything from bird wings and fish fins to insect wings and even plant structures to find new ways to improve aircraft design. For instance, they're looking at how birds can change the shape of their wings in flight to achieve both agility and efficiency.
So we could see aircraft with morphing wings that adapt to different flight conditions. That's amazing.
Exactly. And they're also looking at ways to create surfaces that mimic the texture of shark skin, which is incredibly efficient at reducing drag in water.
Wow, so we could have planes with shark skin. It's both cool and a little creepy.
Yeah, it's definitely an interesting concept. But the point is that nature offers a wealth of inspiration for engineers looking to design more efficient aircraft.
Well, I think it's safe to say that our deep dive into high aspect ratio wings has been a wild ride. We've gone from the familiar to the futuristic, exploring everything from strut-braced wings to twin-fuselage aircraft to planes inspired by birds and sharks.
It's been a whirlwind tour of the cutting edge of aviation, and it's clear that the future of flight is going to be incredibly exciting.
Absolutely. And who knows, maybe someday we'll be boarding planes that look more like birds or spaceships than the aircraft we see today. But before we wrap up, I have one final question for you and for all our listeners. With all these mind-blowing innovations on the horizon, what do you think the airport of the future will look like?
Ooh, that's a great question to ponder. Imagine giant futuristic terminals designed to accommodate planes with shapes we can barely even conceive of right now.
Right, and maybe those terminals will be powered by renewable energy, and the planes themselves will be whisper quiet and emission-free. The possibilities are endless.
I can't wait to see what the future holds for aviation. It's going to be an amazing journey.
Me too. Until next time, keep those imaginations soaring, and remember to always keep exploring the world with a sense of wonder and curiosity.